All right, why don't we go ahead and get started? So welcome back everybody to EE240. So today we'll finish up with some of the high-speed filtering stuff that we were basically the equalizers that we had talked about last time. We'll also start talking about some comparators. Just perhaps this is obvious based on the level of attendance at the moment. Phase 1 of the project is due this afternoon. Phase 2 is due basically a week from tomorrow. So even if you finish that up, make sure you kind of get going on Phase 2. Both of them should actually be fairly straightforward, but they're both sort of ramping up in complexity towards the final phase of the project, which I'll post up actually pretty shortly just so that you kind of have an idea of what we're going to be talking about there. But basically, as I said, make sure you really do get going because those things basically will ramp up very quickly and it always goes by much, much faster than you expect. I think the final phase of the project has about 2.5, maybe almost 3 weeks of sort of time for you to kind of really wrap everything up there. So, any kind of questions on either the project or stuff we've been talking about so far?
This is a scheduling question. Our presentations are going to be on the Friday of the off week.
That's right. That's right.
Okay.
So actually, we'll be holding lectures that week, just because I don't think there's any other way that we'll really get to cover all the time. The good news is this is a grad class, so I can do that without being publicly flogged. Unless anybody has some major objections, which I don't expect there will be, that actually gives us some time to kind of cover up the last sort of couple topics that we probably won't be able to get to until then. And then, yes, the presentations will indeed be in that sort of Friday of I think it's the RRR week.
Okay.
Any questions? Or yeah.
Yeah, so in the second phase of the project, you're going to implement, suppose we choose the architecture with the feedback. So doesn't the amplifier gain need to be changed in that case? Like all these things are not valid,
up
right?
to you. So you get to figure out what it is you really have to do to make the system work, right? So that's kind of the point of this project, is for you to actually figure out, okay, based on the higher level specs that I gave you, what does that actually mean for your amplifier? So that's actually kind of the point. So indeed, you may need to actually change the DC gain over what you had used in the previous phase of the project. You could also just change the transmitter swing. Again, up to you to decide which one of those is actually the right thing to do. Yeah?
Can we email you the voltage outputs?
Yes, thank you for reminding me. So for phase 1 of the project, if you haven't already, email me the voltage outputs. In fact, if you want, you can email me the reports and everything like that as well, but definitely email me the voltage outputs. Any other kind of questions on either material or project or anything like that? Okay, good. So if not, let's actually go ahead and sort of dive back into where we were last time. So last time we sort of just basically had finished talking about the RC degenerated equalizer, which just as a reminder sort of looks something like this, right? So there was some, let's say, RS, some CS here, and we're basically just using that to degenerate the input devices. We said that this was an interesting way of doing things because by doing this, we were going to create the equalizing function that we wanted without really spending any extra power to do so, right? As opposed to, for example, the amplifier, the additional amplifier and feedback, we actually had to spend extra power to create that transfer function that we were interested in. So just as a reminder, if this is sort of how things looked, and let's say somehow magically you had, let's say, ideal current source loads and you had no capacitance whatsoever, then what would the sort of transfer function for this thing look like? Just what would the shape look like? Oh, okay, well, so by the way, I have no capacitors whatsoever, so the shape that you did was slightly wrong, but close. Okay, there we go. Eric's got it. Okay, so basically, we'll start out with some DC gain. It'll have a 0 in it, and then it'll flatten out at some peak gain again, right? Okay, and so let's actually just, I don't know, let's just call this A DC and A peak over here. Okay? That's, of course, okay, so I'll be slightly more realistic. We'll even assume there's some output resistance from those current sources or something like that so that the peak gain isn't actually infinity. Okay, so let's say I went and I told you that the channel that we're talking about is just a first order channel, meaning it just has one pole. And let's say that I told you it has a pole at 1 gigahertz. Okay, so if the channel has a pole at 1 gigahertz, you want to put the 0 for the equalizer also at 1 gigahertz. Okay, so now let's say that I told you that we were operating at 6 gigabits per second. By the way, sometimes I'll do gigabits per second this way. Sometimes people call it GBps. If I do either one of those, it's the same thing. Okay? So let's say that I was operating at 6 gigabits per second. Where would I want to make sure that the pole from the equalizer is? Where would I want to place that? 4 gigahertz. Okay, so now, where did 4 gigahertz come from?
2/3 of the...
Okay, so it came from 2/3 of the bandwidth, but now I actually want to push you a little bit. Because this amplifier I drew here, the amplifier itself has like infinite bandwidth, right? Because I didn't add any caps or anything like that at the output. So the only reason I have this pole here is just that at some point, when that cap kicks in, I can't do anything better than shorting the two tails together. Right? At that point, I've already gotten the full GM from these transistors. So you're right, there's 4 gigahertz that comes from the 2/3, but now I want to just sort of ask a sort of follow-up question to make sure everything is clear. What would have happened if I had chosen this to be higher than 4 gigahertz? What if I'd set it at, let's say, I don't know, 5 gigahertz? So let's maybe even draw that in a slightly different color. So let's say that I had chosen the pole to be at 5 gigahertz. How would things change in terms of the behavior of this equalizer?
Your A peak would be higher?
Say that again?
Your A peak would be higher?
Actually, so is it going to be higher? It would be nice if it was indeed higher, by the way, but is it really going to be higher?
It'll be in 20 dB, right?
Or whatever it is, right? I just gave it at some, I just decided it's some A peak. By the way, what is this A peak? What is that set by? At a really high frequency, what does this thing look like?
GMRL?
Yeah, it's just going to be GMRL, right? So if I'm moving these things around, which is how I would move that pole, I can't move the A peak, right? It's going to be stuck by GMRL. Okay, so if I did indeed actually choose 5 gigahertz, or let's actually make it even more clear, let's say I chose 8 gigahertz. So what am I going to have to pay to make that 8 gigahertz?
Power.
Or ADC?
Okay, well, so actually you guys were both sort of right. So you said power, you said lower ADC. Let's assume that I keep my bias current fixed. If I'm going to keep my bias current fixed, then to make that thing 8 gigahertz, and my drawing's not great there, but pretend that was a straight line, then I would actually have to get an ADC divided by 2, right? In other words, for the same amount of power, if I put the pole at a higher frequency, then actually I would have to throw away DC gain, right? Now, you guys are right, you can change the amount of power and rescale everything, but the point here is that if I set this pole, which is, again, just coming about because of the fact that at high frequencies, the best you can do is make this a short. If you set that too high, you're actually going to be throwing away DC gain, okay? So now, similarly, just to make sure it's sort of, again, clear, based on this, you'd say, okay, well, then maybe what I really want to do, I'll use a different pen here. Maybe what I really want to do is put the pole at lower frequency, because then I could get higher DC gain, right? Okay, so now why don't I want to do that?
Nyquist.
Yeah, it's sort of the Nyquist. It's not really Nyquist. It really just means that if I do this, now I'm going to be filtering my input, right? So if you guys remember last time I had mentioned that you always want to build this thing so that the pole from the equalizer itself lands at the same spot as the actual bandwidth target for your amplifier. This is why. Because basically if you put it too high, you throw away DC gain. If you put it too low, you'll actually be filtering out part of your signal. Okay? It always turns out what you want to do is really place it right in the right spot. In other words, right at the bandwidth that you're interested in. Does this make sense to everybody? Or? Okay. So we talked a lot about sort of this resistive degenerated equalizer, but so far I've only shown you sort of things that have first order responses, meaning that they could fix a channel that has a first order roll-off. Bad news is most channels have much higher order roll-offs than that. Oftentimes at least like 2 poles. Okay? So now what I'm going to want to do is figure out, okay, how can I take this equalizer and potentially add another pole? Or excuse me, add another 0. Okay? So what do you guys think? What are some steps you could do to add another 0 into this equalizer? how could you build something that has 2 zeros? By the way, there's a couple of like really silly answers that maybe are not so bad.
Use an active filter.
Oh, okay. Use an active filter. I think this is an active filter, so we'll see in a second maybe more detail. What'd you say, Dan?
2 amplifiers.
Yeah, I could just take this whole thing and repeat it, right? I can just add another stage afterwards. And then I have 2 independent zeros I can create. Now, that works, and indeed oftentimes may actually be the right answer. But let's say that, I really just want a very slight additional amount of peaking, or I don't want to spend any extra power at all. Okay, I still want 2 zeros, but I don't want to spend any extra power. So any other way you guys can think of to try and create another zero?
The ladder network.
Oh, okay, so yeah, I could try and come up with some more sophisticated network down here. That's actually true. That turns out to usually be pretty difficult. There's one more thing you can actually sort of change here and not spend any extra power.
E through 0?
Okay, yeah, you're right. You could, you could create some sort of feed through 0. Getting the sign right is a little bit tricky. You have to like cross-couple things. That's actually not a horrible idea. There's one more thing that I claim is actually maybe a little bit easier to design. So by the way, we've modified the transconductance. And gain, of course, is set by GM times RL. So what else can we modify?
RL.
Yeah, RL, right? So what we basically have to do is somehow make it so that RL also has a frequency dependence, right? So by the way, actually, what kind of frequency dependence do we want RL to have? Like, what do we want RL to look like? I should really say ZL, I suppose, to be precise.
Short of low frequencies.
Yeah, you want it to have low impedance at low frequency and high impedance at high frequency. What is, by the way, anybody think of a network that does that?
Inductor?
Yeah, it's just an RL, right? Just looks something like this. Okay, now, the bad news is, usually if you actually wanted to do this, the inductance you'd have to use would be ginormous. Okay, especially if you have a small cap. So, usually you're not going to actually be able to do that. Even though actually, if you could use an inductor, there's some advantages you could get from doing that. So instead, what you actually end up having to do is build what's called an active inductor. Okay? So as we'll see in 1 second, I actually claim you've already seen an active inductor. Okay? Because if you remember the very first equalizer I showed you, what we basically did was took a transistor, right, tied it up in a diode connection, but basically stuffed a low-pass filter in the feedback of that diode connection, right? If you sort of think about it, this does exactly what we wanted this inductive load to do over here, right? Because at DC, this thing looks like 1 over GM, but at high frequencies, once the low-pass filter kicks in, it looks like an RO, okay? So now the only extra trick we have to play is figure out how do we basically connect something that looks like this into what used to be this current source load, and basically not burn any extra power. Okay, so it turns out that's actually pretty straightforward, and I'll just draw a couple of those now. So by the way, I'm just going to draw it only as building the active inductor as the load. I'm not going to draw the degeneration, but you can add the degeneration on as well if you'd like to. Okay, so we have our input pair, we have our tail current source, and so now what I want to do is I want to somehow put a diode-connected transistor as my load. Okay, so what's like the most obvious way of doing that? What would you put up at the top?
PMOS.
Yeah, there we go, diode-connected PMOS, right? It's just that rather than making it just a PMOS with that diode connection, I'm going to put a low-pass filter, right? Which would look something like that, right? So, by the way, just to make sure it's sort of absolutely clear, why did I show these caps up here as having the other terminal up at VDD? Why didn't I tie those to ground, for example?
Rejection?
You said something about MOS caps.
Power supply rejection?
Yeah, there we go. Power supply rejection. Okay, so by the way, maybe MOS caps is a good idea too, but actually, remember, it's a PMOS transistor. So this gate point here is always referenced to the supply. It's always referenced to the source. So we want to make sure that VGS is constant. Better tie this cap up to VDD. Okay? But other than that, indeed, this is exactly the sort of active inductor load that we just talked about. It's just that now I'm not spending any extra bias current to do it. Okay? Now, as we'll see, and actually maybe you've seen already, for a lot of these sort of high-speed link kind of things that we're talking about, they're pretty high-speed circuits. And if you kind of think about it, the reasons we generally don't like PMOSs in high-speed circuits is because their FT is lower. Right? In other words, they're going to introduce more capacitive loading than we would have introduced if we could have, for example, used like an NMOS transistor. Okay? Well, so it turns out you can actually build an active inductor using an NMOS transistor also, and still without burning extra bias current. Okay? So this is going to look a little bit funny at first, but we'll see how this works in 1 second. So imagine that somehow, I'll draw it this way. Imagine I just took for my load, and rather than putting PMOS transistors, I put NMOS source followers. Okay? Seems a little bit odd, right? But okay, so we'll see how we'll fix this in sort of 1 second. Okay, so at DC, what would be the impedance I see looking up into there?
1 over GM.
Yeah, 1 over GM. I mean, by the way, actually, I guess the way I drew it, it would almost always be 1 over GM, right? Okay, but so now, what I wanted to have happen is that for higher frequencies, I wanted the impedance to go up, right? Okay, so now, turns out, all I have to do is add a little bit of resistance right there. Okay? Why is it that adding a little bit of resistance there makes the impedance go up at high frequencies?
You will filter off the gate voltage, so
Okay.
the amount of current which goes in is much lesser. So it's
You're right, but I guess physically, what's the element that I'm missing to draw here to show why it is the impedance actually goes up? Yeah, so there's always a CGS, right? There's always a capacitor from the source, from the source up to the gate. Also, if you think about it at high frequencies, remember the reason why we said this is 1 over GM was because we said the gate was fixed and the source voltage was moving around. Well, at high frequencies, when this capacitor shorts out and makes the gate and the source voltage fixed, that means the GM doesn't see any change in voltage, right? In other words, the voltage across that GM is fixed. So now at high frequency, just like with this one, the output impedance goes to like RO, right? And so again, we have exactly this active inductor load that we were interested in. Okay? So it turns out you can do both of these. Perhaps you can get a little bit higher speed with this, but obviously the common mode coming out of here is very different than the common mode coming out of there. If you wanted a high common mode, you might even need voltages like outside of the supply rail or something like that. But potentially you can get higher speed out of this particular design here. Okay? Does this make sense to everybody? Or? So again, I mention these because in your project, you indeed may find that you need a couple of zeros in your equalizer. And so if you do, you may want to find ways of basically combining together a couple of the techniques that we've talked about to actually go ahead and implement that. Of course, the interesting question will be, what are the trade-offs between them in terms of noise performance, in terms of, as an example, power consumption, and so on and so forth. But that's kind of the point of the project for you guys to figure out. So any kind of questions on this? Or? Okay, so before we completely move on, I just wanted to mention sort of one quick thing, which is, so far I've basically been saying something like, okay, I gave you this channel. And you know somehow magically that this is, let's say, 1 gigahertz. But in reality, if you think about those pictures of the big PCBs that I showed you, there was all these wires running around all over the place, right? With lots of different lengths and probably going through different vias and so on and so forth. So in reality, what you usually have to do is you have to build a link, meaning build your link circuits, so they don't just work over this one particular channel, but they work over a bunch of different channels. So you may have another channel that, let's say, looks like that. You may have one that's really, really nasty that does that, right? In other words, the characteristics of the channel are going to move around all over the place. What that basically means is we'd really like to have a way to make it so that when we build our equalizer, we can actually tune it, right? We can actually move the locations of the poles and the zeros around, okay? So in order to do that, and I'm just going to draw things sort of conceptually with our active inductor load, but the idea is very similar for the other cases as well. So if we wanted to do something like that, what that basically is going to mean is we're going to have to change any one of a number of basically 3 different things, right? So I guess maybe just first of all to be clear, what sets the sort of 0 for this particular equalizer? What frequency is that set at? Well, I should say for this active inductor. What sets the 0 there?
The cap?
The cap, and what else? So what frequency will this thing start to look like a higher impedance? If I looked at the Z. I think somebody said it. Just repeat it.
1 over RC.
Yeah, it's just 1 over RC, right? Because that's the frequency at which the low-pass filter kicks in, and so you get less feedback onto the gate and basically you get less effective GM, right? Okay, so if that's the frequency of the 0, then if we wanted to be able to tune the location of the 0, that basically means you either need to tune the resistance, tune the capacitance, or both, right? In fact, actually, if you really wanted to be able to like change the DC level and maybe even the magnitude of the peaking, you might even want to be able to sort of tune the effective GM of your transistor too. Okay? So what I'm going to do is just sort of sketch a few quick things as to how you can actually go about doing that tuning. So, as you might imagine with sort of all of these things, you can basically do that tuning in either an analog way or a digital way. Okay, and a lot of times you'll probably actually want to do it the digital way just because it's sort of easier for the rest of the system to do it that way. So I'm just going to draw sort of both, just so you have an idea. You won't necessarily actually have to do this in your project. In the past, I used to make people do it, but this is more just sort of for your information. Okay? So, for the analog, let's say I wanted to tune the resistance. Well, that's, I guess, perhaps sort of obvious. I could just take a transistor. If I use that transistor in the triode region, but I just move the gate voltage around in sort of an analog way, then effectively I'll be tuning that resistance along with the gate voltage, right? Now, the only problem with this is that because it's sort of just based on the device characteristics, when I move that gate voltage around, I may not really know exactly what I'm setting the resistance value to. So you'd have to somehow sort of come up with some feedback loop that was telling you, okay, what's the magic voltage I need to actually set my equalizer 0 to like sit somewhere over here, let's say, right? So that may be a little bit of fun. If you're interested, come bug me. I can sort of show you a couple of ideas. But in contrast, if I built this thing in a, let's say, digital way, then I might do something like the following. Okay, so essentially what I'm going to do is I take my sort of big, let's say, polysilicon resistors. Let's call that D0 and we'll call that D1. Okay? I take some string of big polysilicon resistors, and if I want to reduce the resistance, meaning I want to change it, I just turn on some switch that basically shorts that resistance out, right? So now as an example, if I did this, and if I turned on D0, I would have half of the resistance. If I turned on D1, well, okay, maybe it wouldn't exactly be half. It'd be like whatever the resistance, the series resistance of those two switches are. Okay? But at least if I do things right, I can at least sort of set it up so that the ratios of resistors are reasonably well known. Okay? All right, so that's sort of easy. Okay, how about for changing the capacitor? And let's maybe start with the digital one because that's a little bit easier. How could you do that? Okay, when you say switch cap, what does that mean?
Switches to add capacitance in.
Yeah, okay, so basically, I could just put a switch in series with a cap, then tie a bunch of these caps up in parallel, right? So again, let's say D0, D1, and so on and so forth. And so the more of those switches I turn on, the more of the caps will actually be connected to the output. Okay? So by the way, it turns out you can actually do something sort of similar, at least conceptually, although not exactly the same, by doing something like this. Okay, this one doesn't really exactly change the cap. It actually is varying like a series resistance that's like, or really it's varying a resistance that's in series with the cap, but it kind of roughly has the same effect in terms of changing the impedance of that cap. Okay? Yeah.
How do you know where the 0 needs to be in the first place?
Ah, so you mean like in the class, or you mean like in real life?
Real life.
Ah, great question. So in real life, what you basically have to do is you have to build some sort of circuit that measures basically what's the frequency content of the data going into you, right? Now, there's a lot of different ways you can do it. There's a lot of sort of clever things that people have come up with. But just as an example, let's say that you knew you always had, let's say, like a first-order low-pass channel. Then one of the very simple things that people do is they basically will do something like the following. They'll take they'll take the input signal, they'll feed it through a low-pass filter, and also basically feed it through a high-pass filter. Okay? Then what they do is they look at the magnitudes of those two signals. Okay? If they're not the same, so that's a plus and a minus, if there's any difference there, and by the way, this is like you take your channel and then you pass it through your equalizer. So if there's any difference between what you see at low frequency and what you see at high frequency, that means you haven't tuned your equalizer to have the 0 in the right spot, right? So what you basically do is you take this and you feed it back to tune the equalizer, right? Now, when you choose what's low and what's high, obviously you have to be a little bit careful, right? So that you know that you've always placed that in a spot where you're likely to hit sort of the boundary between the high frequency stuff and the low frequency stuff. And you can imagine if there's mismatching, etc., you can get some issues. But conceptually, this is kind of how you could come up with a loop that would do something like this. Absolutely. So this is a closed loop feedback system, right? So you actually would run this continuously on your data.
Okay.
Now, it turns out you can imagine if you're doing this and you have real data, if the data itself is always DC, then by definition, this thing is going to give you 0 output, even though maybe the equalizer was tuned correctly. So with a lot of these sort of tuning loops, you have to make some assumptions about what the characteristics of the data really are. So that's actually a great question. We're not going to spend a ton of time on how you really do this in this class. I'm going to assume that you know what the channel is, and so you can sort of design the equalizer. But in reality, this is absolutely an issue that you have to think about. It's a great question. Any other questions? Or? Okay, so just last and very briefly, just to make sure that, for sort of the sake of completeness, if you wanted to tune, as an example, the GM of that active inductor, that's kind of like saying you want to tune like the size of the transistor. Well, so the way you could do that is doing something like this. And again, I'm going to just draw the digital one because that's a little bit easier. But basically, imagine that this was like your V feedback or whatever. So basically, you could take that V feedback, and either you connect it to the gate of the transistor, or you just shut that transistor off, right? And so then you could take this whole thing and repeat a bunch of them in parallel. So let's call this, let's say, D0, and let's call this the drain. Right, you might have another one that looks like, let's say, that. That's also the drain. And this is, let's say, D1 and V feedback, right? So you can take a bunch of those, basically partition them into different pieces, and then turn on and off how many of those different pieces do you actually use in the feedback circuit. Yeah?
Can you also just use a varactor?
Yeah, that's right. You could use a varactor. So if you have a nice varactor, then, that which maybe would look something like that, you can use that too. You just have to be a little bit careful about the DC levels and things like that. It may not exactly work out the way you want it to. So this you can always build, right? Yeah.
What's like typical power consumption of these types of loops compared to the overall?
Oh, you mean like this feedback loop here, this control loop, or you mean like
including the whole equalizer and everything?
Well, okay. So the answer is I don't know. That's for you to figure out. But you can do a pretty darn good job, right? Because if you kind of remember, you can kind of figure things out based on, okay, just like we had talked about before, what's going to set your power is how much GM you need. right? Okay, well, what's going to say how much GM you need is really going to be the capacitance, right? And perhaps, therefore, the noise in your system, right? So you can actually very quickly go and run just some back of the envelope. Okay, if I have this amount of noise in this capacitive load, or I should say it the other way, if I have this amount of noise, here's how much capacitive load I need to have, and therefore here's how much power I have to actually take. Okay, but ballpark numbers, you should be able to do this in the single milliamp range. Okay, even at, let's say, 5 or so gigabits per second, not even up to about 10 gigabits per second or so.
So it has to run at the same speed as the data stream?
The equalizer itself, you mean?
Oh, that and kind of the other feedback loop.
Oh, no, okay, so this adaptive loop, this thing is usually really, really slow,
Okay. Yeah.
right? Because this is only trying to track what were the changes in the channel. Now, the channel does change, like the humidity changes, the temperature changes, the mechanical stress changes, all kinds of weird stuff changes, but the good news is that's all way, way slower than multiple gigahertz, right? So this loop here usually doesn't take too much power because it doesn't have to be fast, right? It doesn't have to respond to very fast changes and things. Again, great question. Other questions on this, or? Okay, so just one last sort of quick thing, which is a little bit of an aside, but you might find useful. It turns out that oftentimes when you want to build these equalizers, if you want to put this 0 at a pretty low frequency because you have a pretty bad channel, and you don't want to have a ton of extra cap, that tends to push you towards pretty large resistors. Okay? Not only that, you'd really like to know sort of fairly precisely what the value of that resistance is, or at least what's the frequency of that filter, so that you sort of know, okay, for this particular setting, this is where I've placed the 0. Okay? So as we talked about a lot way back in the beginning of the class, building big resistors is kind of painful because they're just big, physically. And they also tend to have a lot of variation. Well, so it turns out there's actually sort of a trick we can play to try and make resistors much more precise. And in fact, perhaps even build very large resistors with very small amount of area. So it's going to turn out the way we can do that is actually to use a capacitor as a resistor. Now, this sounds a little bit funny at first, but in order to see sort of how something like that might work, let's sort of do the following thought experiment. So let's just say I had a normal, plain old resistor, okay? And across that resistor, I put some voltage, okay? Some basically relative to ground V1 and V2, okay? Let's just pretend that I only ran this resistor for some amount of time, okay? And during the time that I ran it, what I want to do is I want to measure how much charge flowed from V1 into V2, okay? So how would we go about doing that? Well, of course, I'm sure you all remember, V is just IR, of course. So the current is just V1 minus V2 divided by R. Oh, but so now I'm just going to run this thing for a finite amount of time. And since I want to know how much charge, what I'm basically saying is, just as a reminder, of course, I is just delta Q over delta T. So I've done nothing here. I've just replaced I. And I can just rearrange things and say, okay, the amount of charge that flowed through that resistor is just V1 minus V2 over R times delta T. Okay? In other words, that's kind of like saying that my effective resistance, or really my resistance, is just equal to V1 minus V2 times delta T over delta Q. Okay? So now, why did I sort of do this whole funky rearrangement? Because what I'm kind of saying here is that what really defines a resistance is how much charge you shuttle between the supplies over a certain amount of time. Okay? And so I claim that actually I can shuttle charge back and forth between two voltage sources without ever actually building a real resistor. Okay? So let's see how I can do that. So now what I'm going to do is I'm still going to have a V1 here. I'm going to have a capacitor, C. But now I'm just going to have like two switches and a clock signal. Okay? So in other words, as an example, when the clock is low, I connect this capacitor to V1. And when the clock is high, I connect the capacitor to V2. Okay? So, if I do that, how much charge is there when the clock, how much charge is on the cap when the clock is equal to 0? In other words, this switch right there is on. How much charge is on that capacitor?
V1C.
Yeah, it's just going to be V1 times C. Okay? When I flip the switch the other way, in other words, I turn on that switch right there. Now how much charge is going to be on the capacitor?
1 minus V2.
Oh, you actually gave me the next answer. I just wanted how much was on the capacitor in this phase. So that's just going to be V2 times C. Right? Okay, so the change in charge, of course, over that cycle is just going to be V1 minus V2 times C. Well, by the way, that change in charge, that's exactly how much charge came out of V1 and into V2. Okay? So now all I'm going to do, since I had said that my resistance could be defined by basically V1 minus V2 divided by the change in charge per unit time, I'm just going to redo that. I'm just going to reuse that exact same equation to figure out what's the effective resistance of this switched capacitor network I drew here. Okay? So in other words, the effective resistance is V1 minus V2 divided by the change in charge, which of course is just V1 minus V2 times C. And so now the only thing I need that's left for me to know is how much time I did this over. So how much time did I do this over?
Period.
Yeah, 1 clock period, right? Okay, well, obviously the V1 minus V2 just cancels, which means that my effective resistance is now just going to be 1 over C times the clock frequency. Okay, and so all I did here was just converted the period to 1 over the period as the clock frequency. Okay? So in fact, magically, just using capacitors, I actually just built a resistor. Okay? So now, why do you guys think this is actually potentially useful from the standpoint of particularly for us building these equalizers? Other than just, okay, maybe it's really easy for me to build small caps, and then if I use a low frequency, I can get a really large resistance. What else is actually kind of nice about this?
You can use it for tuning, like you can shut off the clock. So
Okay, you can shut off the clock, and then obviously your resistance goes to infinity. That's certainly true. What else is kind of good about this?
Filter corner is defined by the ratio of
Ah,
capacitances.
there we go, right? So if you guys remember when we talked about biasing and stuff like that, you remember how I said anytime you want to get something to like track or be forced to like, you know, be set by something that you know what it is? If, as an example, you want to know what a low-pass filter, where the corner frequency is, you need to find something that has the same physical units as what you're interested in. Well, the physical units that we're interested in here are hertz. Well, okay, notice I can create a resistance that is directly related to hertz. It's set by some number of hertz, right? This could be like my crystal from the clock or whatever it is, right? So actually what that means is if I build a low-pass filter out of this, so literally I just take my standard low-pass filter and just replace that resistor with a switched capacitor resistor. So let's call that C1 and C2 now, right? Let's call that V in, we'll call that V out, okay? We just said the effective resistance of that switch cap was 1 over C1 times the clock frequency, right? Okay, so what's the time constant for my filter then? What's that going to be set by?
C1 over C2.
Yeah, you got it flipped, but that's fine.
Yeah.
It's C2 over C1 times 1 over F clock, right? In other words, my bandwidth is just going to be set by C1 over C2 times the clock frequency, right? So now if I actually gave you a clock frequency that was precise, you can set that low-pass filter corner just by setting the ratios of capacitors, okay? So if this was precise and well known, you should be able to do a darn good job with setting that. And now, of course, if you wanted to tune the thing, you could just tune either C1 or C2 and actually shift that thing. And as long as you knew what the ratio of the tuning you were doing was, you'd know very precisely where is the low-pass filter corner that you've set. Okay?
Easy to forget the 2 pi.
Yeah, so I did omega here. So, just be careful. What I wrote, I believe, is correct. So just be careful that there is a 2 pi relationship between the actual clock frequency and the bandwidth. You're absolutely correct. So yeah, I'm pretty sure I did it right this time. But yes, there's the factor of 2 pi there if you wanted to make this F bandwidth. Fortunately, 2 pi is precise also. Any other questions on this? Or? Okay, so as I said, this is somewhat of an aside, but you may find this actually quite useful. Not necessarily, perhaps in this project, but generally speaking, anytime you want to build filters, it's a good idea to know how you've actually what you've actually really referenced that filter to. And in this case, you could reference it to a real clock frequency. Okay, so unless there's any other questions on this, let's actually go ahead and move forward. So the next topic we're really going to talk about, as you might guess, is comparators. Okay, and so the reason really I'm going to be talking about comparators is we've already talked about transmitters. We've talked about what the channel looks like. We've talked about how you might build like the front-end amplifier and the equalizer. So really sort of the last component we need to actually build a full link is the comparator that we're going to use as our receiver. Okay? So just to sort of start things off, when we talk about comparators, there's really sort of a fairly long list of sort of specs and issues that you might really care about. And as we'll see actually very shortly, a lot of times the way we're actually going to build this is with some sort of gain stage followed by a latch. And what I mean by a latch is something that basically just stores the digital data when the clock is low, the previous digital data, and when the clock is high, just passes it through. Okay? So what are some things obviously we're going to care about? Well, clearly you're going to care about how fast can you actually clock this comparator and still get the right answers out of it. You're going to care about offset, meaning at DC, rather than me putting in like a 0 volt input, and right at 0 volts I transition between having a 1 and a 0 at the output, maybe it's actually I have to put in like exactly at 10 millivolts, that's when I flip. Okay? As we had talked about obviously already in the context of the high-speed links. Okay? So I'm going to care about how do I make that offset small, because like we talked about with links, if I have too big of a residual offset, then that's actually really going to eat into my bit error rate performance, right? There's actually another thing which is kind of related to the offset, which is sort of what's known as resolution. So here when I say resolution, what I really mean is once I've kind of gotten to within that offset, like once I've placed myself right at the tripping point of the comparator, how big of a signal do I have to put in to make sure that I really get a 1 or a 0? Because you can imagine if I put in too small of a signal right next to that offset, the comparator itself has some noise, right? That noise means that even though you put in a signal that was maybe greater than the like slightly above the offset or slightly below the offset, the noise could cause it to flip the wrong way, right? So that's kind of what I mean by resolution here. By the way, as you might expect, a lot of these things will trade off with each other. So as an example, the faster you want to make the comparator, the harder it'll be to get very high resolution. As we'll talk about probably not this time, but maybe next time, there's another sort of very interesting thing that tends to happen in comparators, which is they tend to remember their previous decisions. Okay, so sometimes if you happen to get a 1 last time, it'll be harder for you to flip the value of the comparator and get a 0 this time. Okay? In fact, actually sometimes you can even have so-called negative hysteresis where if you had a 1 this time, it really wants to be a 0 next time. Okay? So we'll see that again a little bit later when we get into the details of how you build these things. As you'll see both in your project and actually in the example I'll give in 1 second, a lot of times you care a lot about how much capacitance this comparator presents to the input. For example, like in the equalizer case, the larger that cap is, the more power you're going to have to get you're going to have to dissipate to get a certain bandwidth, right? And then, of course, there's a bunch of other stuff that, the standard stuff you might expect. You care about how much power this thing dissipates. You're probably going to care about how much column mode rejection you have. And as we'll see a little bit later on, comparators have this very nice property that they like to do what's called kick back on their inputs. In other words, if you had a nice clean, like 10 or 1 millivolt signal over there, well, you've got a volt of signal over there, or 2 volts, or however much your power supply is. That means if there's any coupling from here back onto there, you could very easily screw up your nice clean analog input signal. Okay? So we'll see all of these things in 1 second, but just as sort of an additional kind of, let's say, piece of motivation as to why comparators might be interesting. We've already talked about it in the context of high-speed links, but these things are used actually many other places as well. One really obvious place is in analog to digital converters, right? So as an example, you could come up with this so-called flash analog to digital converter, where the idea is very simple. You just have a bunch of comparators. In particular, you have 2 to the number of bits minus 1 comparators. And then what you're basically doing is, if I have some input signal, let's say that looks like that, you're just looking at, okay, is it above this threshold? Is it above that threshold? Is it above this threshold, this one, and so on and so forth. As you can imagine, depending upon how many of those thresholds it's above, that tells you exactly what the sort of analog value of the input signal was to within this particular resolution. So these types of converters, at least in really high-speed applications, are popular because you can kind of see I just have to clock all of these comparators once, and I instantly get the analog, the digital conversion coming out. I shouldn't say instantly, but it takes 1 cycle for you to get the conversion out. Okay? So again, if I want to sort of make these things fast, what that boils down to is I have to make these comparators really fast. But because I have so many of them in parallel, let's say if I wanted an 8-bit converter, I'd have 255 of these comparators. I want to make sure that each one of those little comparators has really, really small input cap. Because if it has too big of an input cap, then when I drive all of those things in parallel, I'm going to have a really huge capacitive load in my input. Okay? So again, just sort of another motivating example for why comparators are an interesting thing to take a look at. And so actually, just in case you don't believe me, let's sort of see why doing this is potentially a hard thing to do. So let's take an example from, let's say almost from our project. So let's say we wanted to build a 4 gigabit per second link. Okay? And let's say also that we want to be really aggressive. We want to make that comparator basically resolve the smallest things we possibly can, just to make sure that it's not really going to have any extra voltage requirement in terms of what you have to put into its input. Okay? So let's say we want to make sure that it resolves, even if I put in just a 1 millivolt difference around the threshold, I want it to resolve that all the way back up to the power supply. Okay? Which in this particular case, let's say that my VDD is 1 volt. So in other words, what I need to do is I need to get a gain of 1 volt over 1 millivolt, in other words, 1,000. And since I want to run this thing at 4 gigabits per second, I better do that in less than 250 picoseconds. Okay? So, just to maybe sort of take a poll and see how many people are paying attention, who thinks that's going to be really easy to do? No problem at all. Hard? Really, really hard? Okay, well, I don't know. How many more adjectives do I need to add to get more votes? Yeah, it's going to be hard. Okay? It's going to be really hard. At least doing it the way we usually think about is really, really hard. So, okay, if I wanted a comparator, I want this gain, I want a bandwidth, I should say, okay, fine. Why don't I just build an OTA? Right? Standard way we talked about. I'll just take some transistor, tie it up to an amplifier. I can get a gain of 1,000, right? And so maybe I can get enough bandwidth. Let's see if this actually works. Okay? Well, like we talked about a few times already, if I just follow my rule of thumb, and I set the bandwidth at 2/3 of the bit period, and I need a gain of 1,000, right? Remember, that's AV0 right there. Then I can just really quickly calculate what's the gain bandwidth product that I need. Okay? So this thing here, that's something like 2/3 of 4 is, I don't know, about 3 point something, right? So what this basically says is I need a gain of 1,000 and 3 point something gigahertz or whatever it is. And so actually, if you work this out, actually maybe I lost a factor of 2 here, but
It's double that.
yeah, exactly. So it turns out I need a bandwidth of, yeah, actually you're right, that is 2.66 terahertz. Okay, so now why are we laughing? Why is this obviously ridiculous with a single stage amplifier? Why is there no chance in hell this is going to happen?
Process guys are going to have to pick it up.
Okay, well, yeah, that's true. It'd be really nice if the process guys gave me some better transistors, but actually, what characteristic of the transistors are we going to specifically complain about?
FT.
Yeah, it's the FT, right? If you guys remember from your plots, maybe, up at the really high voltages, your FT was, I don't know, 120-ish gigahertz or so. Okay, obviously, you're at like factor of 10 over the FT, right? So no way in hell that transistor is actually going to give you any gain at that point. Okay? Now, by the way, just in case you think, oh, well, I gave you a 90 nanometer process technology, and maybe you could do this in like a 22 nanometer thing, and that'll save your butt. Sorry, FT for those is also about a couple hundred gigahertz. Okay, so not going to happen. So the bottom line is, no way in heck you can do this with something like an OTA. But trust me, I've built plenty of comparators that actually achieved this kind of specification. So what's the magic trick you have to play to actually make this happen? What's kind of my assumption that I was making here? Yeah.
You can have many stages to implement the AVO.
There we go, right? So the real trick is, the reason why we think gain bandwidth is so hard to get is because we usually think about single-stage amplifiers, okay? And indeed, with a single-stage amplifier, there's a very stringent limit on what's the gain bandwidth you can get. And it's basically directly related to the FT of the device. But actually, if you take a bunch of single-stage amplifiers and you put them into a cascade, turns out you can very grossly break the sort of gain bandwidth limit, okay? So this actually gets into sort of lots of interesting discussions. What really is happening is that once you have a multi-stage system, for single-stage systems, what was always trading off was gain and bandwidth. But with multi-stage systems, you actually have another degree of freedom. That extra degree of freedom is the delay, okay? So what it actually turns out is that gain and bandwidth don't intrinsically trade off with each other. It's really gain, bandwidth, and delay, okay? Because you can kind of imagine if I have a multi-stage amplifier like this, as I go from here to here, my gain is going up like as a power series, right? My gain is going up like, if this was, let's say, A, then over here, it's going to be A squared, A cubed, A to the fourth, and so on and so forth, right? But my bandwidth, even if I'm sort of pessimistic, will only be reduced by roughly 1/4. Okay, in fact, it's actually even a little bit less than that. So clearly, if A was, let's say, 10, by the time I get here, I've got a gain of 10,000. But I only paid a factor of 1/4 for it in bandwidth, right? Clearly, I've really grossly broken the constant gain bandwidth limit, okay? My delay, trust me, is going to be larger, and which therefore means that doing something like this is probably not a great idea unless I want an oscillator, right? But for a comparator, that's fine. All I need is just to get enough gain and to get the bandwidth that I wanted, okay? So let's just sort of quickly take a look at how would I go about building a cascaded amplifier like this, in other words, a multi-stage amplifier, in order to get the kind of gain bandwidth numbers that we want, okay? And so in particular here, what I'm going to try and figure out is what's like the optimal way to build that cascade of amplifiers to get the maximum gain bandwidth product that I can, okay? So it turns out you can do a slightly more sophisticated analysis than what I'm about to do, but it actually results in a very similar answer. So what I'm going to do is actually use some very sort of simplifying assumptions. So what I'm basically going to do is something like the following. Let's just assume that every stage is basically just my sort of simple resistively loaded OTA. So I have some RL. And it's going to drive another stage over here. That other stage is going to present some CL. Okay? And I'm even going to assume that all of these stages are basically the same. Okay? So I have another RL over here. It's going to drive another stage like this, which gives me another CL. And then so on and so forth. Okay? So if I take this, then now what I'm going to do is, if I want to sort of estimate the gain and the bandwidth of this thing, well, gain, that's pretty easy, right? If I know the gain of each stage, if I have n stages, I'll just have a to the n of gain, right? And don't worry, we'll write all this out in 1 second. Okay, bandwidth, that's actually a little bit more complicated. But to make my life easy, I'm just going to use open circuit time constants. Okay? In other words, I'm just going to say that the total bandwidth from here to here is just the sum of the taus of each stage. Okay? Or rather, I should say, the overall tau is just equal to the sum of the taus of each stage. Which, of course, since all of these are identical, just means that the overall tau is n times larger than the tau of each stage. Okay? Again, not exactly correct, but turns out will give us actually a pretty reasonable answer. Okay, so under this sort of set of assumptions, let's just go and sort of write a few equations down. And in particular, the first thing I'm going to want to do is figure out if I said, okay, here's a certain gain and a certain, let's actually really just say, here's a certain gain that I want you to achieve. What's the maximum bandwidth you could get while still achieving that gain? And therefore, how many amplifier stages should you use to actually achieve that bandwidth? Okay? So let's just sort of start this out. Okay, so the time constant for the stage, of course, that's just RL times CL, right? Nothing magic there. So now to actually sort of make it clear what the final answer is going to be, I'm just going to do again one of these standard tricks where I multiply by GM and divide by GM, apparently arbitrarily, but it's to sort of make a point. Okay? So I'm just going to say that this is equivalent to basically GM times RL times CL divided by GM. Okay? So now hopefully it's clear why I did this, because this basically says that the time constant is just the gain of the stage, GMRL, divided by the gain bandwidth, GM over CL. Okay? And let's all actually call this gain bandwidth stage. Okay. So now that I have this, again, remember my goal is I want to figure out how do I basically, for a given amount of gain, how am I going to find the maximum, what's the maximum bandwidth I can possibly get? And how do I build the amplifier that achieves that maximum bandwidth? So of course, to do that, I need to figure out the overall time constant for the comparator, which, again, nothing magic there. If I have n stages, that's just n times the time constant of each stage, which again is just a stage, over the gain bandwidth of the stage. Okay? All right, so now, since I made each one of these amplifiers the same, if I told you that I wanted a certain total gain, what would I set the gain of each stage to be? If I have n stages and I want a total gain, a total.
Nth root of
Yeah, it's the nth root of the total gain, right? So the gain of each stage would just be the total gain to the 1 over n. Okay? Well, so why am I doing this? Well, because if I take that, now what I can do is I can say that the comparator time constant is just n times the total gain to the 1 over n divided by the gain bandwidth of each stage. Okay? Why is this useful? Well, now what I can do is if I want to maximize something, I take a derivative and I set it equal to 0, right? In this particular case, what I'm basically doing is I'm choosing the number of stages, right? So I can just take the derivative of this tau with respect to n and set it equal to 0. Okay, so actually, before I dive in and start doing that, just out of curiosity, does this look sort of familiar to anybody? So there's at least, I don't know, about 10 of you or so that I know it should look familiar to.
Is it like the inverter chain?
Yeah, exactly. This is exactly the buffer chain optimization problem. Okay? This is exactly like just taking a chain of inverters and asking what's the fan out that you need on each stage. Now, if you haven't taken 141, don't worry. We'll go through the rest of the result. But just, this should pop up in the back of your mind. Actually, this is a problem that should be very, very familiar to many of you. Okay? So just to sort of see what the final result ends up being, if we take that derivative, then we just get that essentially we want A total to the 1 over n divided by the gain bandwidth of the stage minus n times 1 over n squared times natural log of the total gain times A total to the 1 over n divided by the gain bandwidth of the stage. Okay? We want that whole thing to be equal to 0. Okay, I didn't do anything sort of fancy over here. I just took the derivative of that expression with respect to n. Okay? The good news is that actually this term right here is the same as that term right there. So I can actually simplify this pretty substantially. Everybody done writing this down, by the way, or just raise your hand, I guess. All right, I'll take that as no major complaints. I can move to the next slide. Okay, so that equation basically just simplifies to 1 minus 1 over n times ln of A total should be equal to 0. Okay? Well, so from that, should be really, really obvious that what this tells you is the number of stages should be equal to the natural log of the total gain. Okay? So now this is, again, where this should start to look really, really familiar. Because what this really means is that if I do this optimization, it tells me that the optimal gain for me to use for each stage is actually E. Okay? Because all that this says is if my number of stages is the natural log of A total, that means the gain of each stage is E, right? The natural number. Okay? So that's my gain. And therefore, my bandwidth, if I just use that gain, is going to be the gain bandwidth of my stage divided by E times the natural log of the total gain. Okay? Because notice this right here, that really is just basically the number of stages. Right? That natural log of the total gain, that's just the number of stages. E, that's just the gain of each one of my stage. Right? In other words, the bandwidth of one stage is gain bandwidth divided by E. I have n equal to the natural log of A total. That's where I came up with this. Okay? So why did I bother writing this slightly complicated but not too bad expression? Clearly, bandwidth does not linearly trade off with gain. Right? Because remember, single stage amplifiers, you would have said that A times bandwidth should have equaled gain bandwidth. Well, now, bandwidth times natural log of gain is equal to the gain bandwidth. Right? In other words, if I want more gain, I can get tons and tons of more gain and pay only a very mild penalty in the bandwidth. Right? Because even if I, let's say, doubled the amount of gain, I'd only be paying even less than like one, well, I should be careful here. Obviously it depends on what the gain was to begin with, right? But if I had a really big gain to begin with, even doubling it only sort of adds 1 E of loss in terms of the bandwidth, right? So maybe actually just to be really clear, let's maybe go through an example here. So let's actually go back to that comparator that we had before. Let's say that we wanted to achieve a gain of 1,000. How many stages would you use? What should n be? Okay. By the way, how did you get to 6?
Take the natural log.
Yeah, you're right. But so I actually
3.
claimed that there was a simple rule that we talked about that may make your life a little bit easier.
2.3n.
There we go. So remember when I said that it's 2.3 tau per decade for settling? It's the same thing here, right? Every factor of 2.3 gives you an order of magnitude. Okay, so I need 3 orders of magnitude here. So basically that's 3 times 2.3. So roughly speaking, I need 7 stages. By the way, you probably really do need 7 stages because 6.9 stages I'm not exactly sure how you build. Right? Okay, so I'd use 7 stages for this thing. Okay, so if I have 7 stages, what would be my bandwidth? And let's just say that for each one of the gain bandwidths of these things, since it's just one stage driving another, let's say that this thing is, for each stage, that's just, I should say, omega t. Okay? So what would the bandwidth be?
T over 7e.
Yeah, it's omega t over 7e, which is roughly like omega t over, I don't know, about 16 or so, right? So in other words, if you had an omega t of 100 gigahertz, you'd have about, let's say, I don't know, 7 or so gigahertz of bandwidth, right? Way more than enough for our 4 gigahertz link that we just talked about. Okay? So now actually, just to be totally clear, let's say that I wanted to even make this gain 10,000. What would be the bandwidth we could achieve? I don't need a number, by the way, just, in terms of omega t. Roughly.
Omega t over 10e or so?
Yeah, it's omega t over 10e, right? So it's omega t over about 20-ish, right? 20, whatever, 3 or 4, right? That's not too much worse than omega t over 16, right? And I just upped the gain by a factor of 10, right? So very clearly, I can very grossly break the direct trade-off between the gain and the bandwidth. It's not that bandwidth doesn't go down if I increase the gain, but it goes down much more slowly than what we would have thought from our sort of single-stage analogy, right? Now, by the way, in case you're curious, it actually turns out that if you really do the optimization and calculate the bandwidth the right way, it actually turns out that the bandwidth trades off with the square root of the natural log of the gain. Okay, not the natural log of the gain. In other words, it's an even weaker trade-off than what I've shown here. The real trade-off turns out to be versus delay. Okay, but if you're interested, I can sort of point you to a couple of references as how you get really that derivation. But turns out, bottom line, this actually tells you about the right answer. Okay, so now we have sort of an idea. Oh, yeah.
So in this derivation, you assume that each stage has got the equal gain. So do you think there may be some other optimization where you have different gains for
Okay. So it's a good question. So if my load capacitance and my input cap are basically the same as each other, then you can kind of think about it. There's no reason why any of these should be different, right? Because if you made any one of them, let's say, slightly lower bandwidth, it would limit the bandwidth of the whole network, right? If the load cap is a little bit bigger than the input cap, then you might actually start playing some games in terms of the sizes of these things. But it actually turns out, the reason I even mentioned the buffer problem, by the way, is because you can actually use almost exactly quote-unquote logical effort, or like the digital sizing problem. You just have to sort of notice that here, what we called fan-out was gain. Okay? But so if you wanted to like extend this to analog, all you have to do is you have to sort of define a new fan-out, which is gain times the actual capacitive fan-out. Okay, and in fact, you can even extend this a little bit more. You can start playing with the V stars of the stages, right? And actually, if you do that, again, you'll pretty quickly find out. You can very directly just modify this and basically get the right answer. So it's a great question. Other questions? Okay, good. So we sort of have an idea as to how we would go about actually building this now. And what we've basically said is that if we want to build a comparator, then what we should be doing is building a bunch of single-stage amplifiers and tying them up in a cascade. Okay? Let's just take a look at sort of what that would mean from a power consumption standpoint. So from a power consumption, obviously, power is sort of proportional to the GM, right? Because that would set sort of how much bias current I need to use. So what would be like the total GM that I would need for this comparator as a function of the total gain that I want to get? So again, if let's say I told you there's some A total that I want, what would be like the total GM that I would have to spend in this chain of amplifiers?
Your load cap is?
Okay, well, let's just assume that I told you that each stage has a certain GM that I've decided based on the load cap. So what would be the total GM I need in the entire cascade?
4.
Say that again?
N?
N. Well, okay. So what is N as a function of the total gain? How did I choose n?
Oh, natural log.
There we go. So the total GM I need to spend is the natural log of A total times the GM of each stage. Okay? I claim this is actually a little bit wasteful. Okay? Because, okay, yeah, I can get a lot of gain, but I have to multiply up how much GM I'm spending to do it. Okay, so if I wanted, as an example, a gain of 1,000, I need 7 times that GM. So I claim I can actually get away with doing it with just 1 GM. Okay? So here's the trick. And so I'm about to do something that you were always told not to do. So if I want to do it with just 1 GM, conceptually, I could just take my GM stage, I take my input, and then once I've amplified it up, why don't I just take that thing and shove it back through the same GM stage, right? So in other words, when I start out, okay, first I get a gain of A, then I go back, I have A times V in, I pass it through A again, now I have A squared times V in, and so on and so forth, right? So in other words, and by the way, just to be clear, I really do mean plus on both sides here. Okay? So in other words, I'm going to tie this thing into positive feedback. Right? So I claim this is actually from a gain standpoint, in fact, from almost all functionality standpoint, basically identical to what I've drawn up here. Okay? And so the way to see that, again, just in case you sort of don't believe me, just think about sort of what happens over time. Right? So when I first put this thing in, roughly speaking, 1 tau later, at the output, is going to show up A times V in, right? Okay. If I wait another tau, that's kind of like saying I've given myself time for the output to go back to the input, right? And get fed back through the amplifier again. Well, now I'm going to have A squared times V in, right? Okay, if I wait 1 more tau, now I'm going to have A cubed times V in, right? So in other words, what I'm really doing here is I've just taken this long chain of amplifiers and wrapped them on top of each other, right? So now, why is this really good news? What's like the great thing about this, which I kind of set up to begin with?
I'll let
1 GM.
Yeah, I only need 1 GM, right? My total GM is just that 1 GM. That's pretty cool, right? Because now I can actually get these ridiculous gain bandwidths we were just talking about, these using only just that one stage, right? So as you can imagine, if I'm going to do something like this with sort of positive feedback, even though usually you were told, okay, don't do positive feedback, it's unstable, it's bad, here, that's kind of what I want, right? I want to take something that's really small, and I don't care how small it was, I just want to rail it out and hit one of the supplies, right? So I have no problem with just basically amplifying the signal over and over and over again, right? It's exactly what I was kind of intending to do with this comparator in the first place. So let's just see sort of how we would actually build something like this. It turns out usually when you want to build positive feedback, it's sort of the really easy way to do it is in the differential circuits. So I'm going to sort of draw that. So basically, let's say we had like in one OTA, we have the other side of the OTA, so this is sort of pseudo-differential. So if I want to tie this in positive feedback, what I should basically do is take the positive output and tie it to the negative input. Take the negative output and tie it to the positive input. Okay? Or excuse me, the positive output to the positive input, the negative output to the negative input. Right? Which, if you work it out, is basically what I drew right there. Okay? Now, what I've drawn right here is kind of like, it's just a latch, right? It's just going to go one way or the other. So it doesn't exactly sort of work as a comparator just yet, because I haven't figured out any way of actually getting the input signal in yet, right? Okay, so to do that, at least just conceptually, let's say I take VI plus, and I just add some switches or something over here, okay? So what I'm going to do with this is I'm basically going to say, initially, let's say at t less than or equal to 0, I'm just going to turn on those switches, and basically, and let's call these C here, I'm going to initialize the caps to VI plus and VI minus. Okay? So that's sort of how I'm going to force the input in. Then once I actually want to get the answer, I turn off those two switches. And so now this thing is just going to start acting like a positive feedback loop, right? Okay, so if I wanted to write an equation for the differential output voltage versus time, what would that be? How would it evolve over time, given that I have this like positive feedback loop here? What would that be? Yeah.
It will be exponential with GM over C.
Yeah, it's exponential with GM over C. Okay, so it's e to the t times GM over C. There's just one factor that I needed to sort of put in front of this thing.
Negative?
Ah, no, so is it negative?
No.
It's not, right? I put it in positive feedback. It really does grow exponentially with time. There's just one other thing that I need in front of this.
VDD times 1 minus.
Ah, is it a step? So you were thinking of sort of like a step response. But where does this thing actually start from? How did I initialize those caps?
V.
That'll be V in times.
Yeah, it's the VI differential, right? Because remember, the 1 minus thing, that's when you put in a step. What I've actually done here is initialize the two caps. So I've put this thing into some initial condition and then let it go. So I'm just letting it evolve from that initial condition. So if you guys remember like your differential equations, this is like the unforced or the homogeneous solution. Long story short, you just take whatever the pole is, it evolves with e to that pole times the initial condition. Okay? So why do I mention this? Because obviously, the smaller the initial differential signal you put in, the more time you need to actually rail that all the way back to a fixed value, right? Which again makes perfect sense because all we were doing was, if we needed to have a smaller input signal, that means we need more gain to get to a certain swing at the output. That would have meant we needed more stages, okay? Here, more stages just means more time, because I need that time to circulate through the loop, right? Okay, so actually Shiva already sort of answered my question, which was what was that time constant? It is indeed just GM over C. Okay, because you can kind of think about this, this sort of looks like a diode-connected device. It's just that the GM is actually negative, right? Because I've tied it into positive feedback and not negative feedback, okay? So what's interesting about this is this basically says the amount of time it takes me to regenerate is just going to be natural log of the total gain times C over GM, right? Okay, so what does that kind of tell us about how we might want to build this? What's kind of going to be like important from the standpoint of minimizing this regeneration time, which is going to set how fast we can actually run the comparator? What's kind of the only thing we have available to us? From a design standpoint, what,
GM?
is it just GM?
V.
It's GM over C, right? Because, by the way, even if I had nothing else, let's look at this side right here. What's the capacitive load going to be set by on this side? It's the CGS of that transistor, right? In other words, this C over GM here, if I do nothing else, is just going to be 1 over omega t, right? Because that's just set by this GM driving effectively its own capacitance on the other side. Okay? In other words, that tells you when you build these things, you really want to use as high of an FT as you possibly can. And you want to make sure you minimize the amount of extra loading you introduce here. Now, there's one other actually interesting thing which we'll talk about in more detail next time. If I'm really totally limited by FT, does doubling the size of both these devices make me go any faster? No, right? Because I doubled the GM and I doubled the cap, right? So resolution time-wise, doesn't help me any. Okay, so you'll actually see with a lot of these comparators, they're basically self-limited. In other words, the only reason you want to size these things to anything other than sort of minimum is because maybe there's some other fixed parasitics caps in the system. And you want to just make sure you're big enough to overcome those fixed parasitics. Okay? There's actually one more reason which has to do with offset, but we'll talk about that a little bit later. With a lot of these comparators, you have a very strong motivation to actually make these devices basically as small as you can. Okay? So there's actually, of course, one more thing here, which is usually if I really was to have these switches that would drive the input like this, these transistors would fight against the input. You'd be sucking current out of the input. You generally don't like to do that. So what we'll see next time is basically how do you actually build comparators in a way that really will let you do this kind of regeneration, but doesn't actually suck current out of the inputs. So we'll do that next Tuesday. So see you guys then.